Okay, let's get to it. Chapter 4 today. I made good progress yesterday, I would say. like, yeah, I look back at the streaming thing. I think I spent like 2 or 3 hours, and then I go through 3 chapters. So on average, on average is like 1 hour per chapter. But of course, it's not even because like this chapter is different. But now we are doing ownership, which is like I think is a famous thing um in Rust that the ownership is very different from other languages. So we're gonna get to it. So if you hear some like background noises because there's a helicopter like circling around my place, and I have to keep the window open. It's so hot here in London. So sorry about that. If you hear helicopters, we experience the same thing together. So yeah, memory save guarantee. So ownership is very important, I guess. Unique feature. So without needing to, so there's no garbage collection needing. That's why it's like good. It's yeah, it's is what Rust is famous for. Important to understand ownership work. Okay, okay. So we're learning it quite early actually. Like chapter 4 is quite early. Like consider we have like 21 chapter in the whole thing. Well, 21 is appendix, but like still it's a big book. Right. So borrowing slices how Rust lay data out in memory. Cool. Let's jump into it. So what is ownership? Oh. So how a Rust program manage memory? All programs have to manage the way they use a computer's memory. So yeah, like I think how Python or C, actually C Python, right? So how C work is that you have to have a reference if you have stored something in the heap, and then yeah, if there's no reference to that thing, like you have to free the memory. So collection, like garbage collection. Regular look for no longer use memory. Yeah, if it's no reference, it's no longer use. Allocate and free the memory explicitly. Memory is managed. Rule the compiler check. So Rust had some like kind of system, so the compiler would check what's going on. So if rules are violated, so it's kind of like safeguarded from the compilation. So if it's compiled, it's probably already followed those rules. That is probably memory safe. So that's why Rust is so robust, like in kind of like memory safety. None of the feature of ownership will slow down your program while it's running. I think that's a myth that they're trying to bust here. So yeah, the feature of ownership will not make your program go slow. It's a new concept. That's why it's everybody mention it, and you have to learn it. Take some time to get used to. So we have to learn those rules. So very common data structure. Oh, we're talking about strings now. Yay! Stack and heap. Yeah, so stack and heap. I think I looked into it a little bit because I was giving a talk about memory. Yeah. So normally we won't think about that unless we really want to look into how memory work in programming. In the systems, we're going to like Rust. So in Rust, we have to maybe think about that a little bit more. Yeah. Right. Let me quickly read this to see if I was correct or not. I have to clear up some of my concepts as well. Stack store values in order to get them and remove the value. Yeah, so stack store them like in order. So there's an order to it. So last in, first out. So it's a stack, basically. No. It's a stack of plate, yes. Yeah, it always works on the top. So last in, first out. Popping of the stack. So pop it from the top. Then heap is not organized. Heap is basically just a free space that you could use. Yeah, so the memory allocator will find an empty spot in the heap that is like big enough for your thing. And then mark them. So it's kind of reserved that to you, and they give you a pointer. So then you have an address of the memory. So allocation on the heap is allocating Yeah, so it's allocating of memory. Yeah. You can store the pointer. You have to follow the pointer. So if you lost the pointer, you lost that thing. Oh. Yeah, you sit at a restaurant. So you have a number, you have a table. Pushing to the stack is faster than a heap because you just dumped it there, I guess. Yeah. Never has to search for placed. What's the top of stack? Currently allocating space on the heap require more work. Oh no, yeah, because stack is just like you don't have to like find the space and give you the pointer, right? Just put it on the top of the plate. So there's only one place to go, is the top of the stack. But for a heap, then you have to go to like find a table, right? Like which table is available, have enough seats that we can all like sit on it and stuff. So yeah. So accessing data in the heap is also slower. Yeah, because you have to use the pointer and found it instead of just basically stack is a fixed location, right? There's only one place to go to access. The others are not available. Yep. Okay, when you call a function, the value passed into the function. The pointer, the data, the heap. So anything passed into the function is actually on top of a so it's put on the stack. So if you, for example, put in a reference, that's probably put in a pointer, so that also get put on the stack. The function is over, the value got pop up. So yeah, it's because when you enter a function, it's probably the first thing that you end, and then you removed it. So if your function calling another function, it's just like it just works well if it's a stack. So keep track of what part of the code user data. Oh. What data using on the heap minimize the amount of duplication. Yeah, so if you're probably using the same data, you probably want to just like have to use the same pointer, just access the same memory, so you don't have to duplicate. Yeah. Just like remember in the old days when you use pandas and copy a data frame and create another one, it's just like blow up your memory very soon. So yeah, you don't want that. You don't want to copy everything. Clean up and use data. Yep. Don't want enough space. Understand ownership. We don't need to think about stack and a heap very often, but now you understand. Okay, cool. Ownership rules. So each value in Rust has an owner. Only be one owner at a time. If the owner go out of scope, the value will be dropped. So each value has an owner. The owner, it can only be one owner, and then if the owner is gone, then the value is gone. What does it mean? So if you look at this one, main function. So they are now talking about scope. So scope is important apparently. So that's s equal to hello. So yeah, before it got declared, it's not valid. It's not declared. It's valid because it got declared and do stuff with s. And if it exit the curly bracket, that the scope is over, and then s is also gone. Yeah. So all the curly brackets are actually a scope, and then before if that got this declare is not in scope, if it got put like using let or whatever, then like it come into scope until it reached the end of the scope, then it's gone again. Right. The string type. Okay. So the data type. Okay. Now we talk about string. It's a great example, okay? So string literals are basically this kind of double quotation thing, this hard-coded opinion, but they aren't suitable for every situation. to take a user input and store it. Yeah, this is the string with the capital S. Looking at heap. The from function. So you're creating a string type with a string literal. Double colon operator, so find the namespace and find the from function under the string type. Okay. It's kind of, yeah, it's a method, so from is a method. And so these kind of string can be mutated. So you store as a mutation. So we can store as a mutated variable, and then we can change how it looks and work. So you push string, so you kind of push this after, I guess. So hello, comma world, I guess. Yep. Yeah. How to type deals with memory. So okay. The contents, the compile time, the text is hard-coded directly. So things that hard-coded means that the compiler knows what's going on. Like there's no unknown for the compiler. Directly into the final executable. Fast and efficient. Yeah, so they are immutable, because if they change, the compiler won't know what's going on, so it's not a thing that what it should be. Yeah. Yeah, so if the size is unknown, then we can't put that like into the memory, so we can't compile that. Yeah. Yeah, the size may change. So like imagine if you had like if the so the hard-coded like string literals, they have a fixed memory, right? Because they are not changed, they have a fixed size, and you know, so when you compile the program, it's basically a fixed size. Like you can't have a program that have variable size depending on like, you know, the size of the strings, which is like weird. So you can't do that. It's like physically impossible. Yeah, so because like this string type is mutable, so that will actually not like that's not hard code in the binary, so it's like something else. So we allocate another memory on the heap for this string type. So compile time, like it compile, it doesn't know how much memory we're using, but it's just that we know that we'll allocate some memory for it when we run the program. Must be request from the memory. Yeah, it's allocated at runtime. So the memory is allocated by the memory allocator, probably your operation system at runtime. Need a way to return this memory to the allocator when we're done with our string. So yeah, we have to also erase it when we are no longer needing it. So to put like give it back to the allocator. So first part is done by us. So when we call this string ::from is actually requesting the memory. So this is happening at runtime. So instead of the hard coding thing, which everything is done by the compiler at a compiler time, this is not. This is by runtime. So it's done by your program. The second part is different. Yeah. So if you have a garbage collector for those languages, that the garbage collector will keep track and then clean up the memory, and it's not needed. For example, like Python, you know, if there's not like if the reference is only one and we're removing that reference, which means that we are no longer needing it, then the garbage collector will come here and remove it for you. Yeah. But if the language is without a GC, then the coder, the programmer, need to is their responsibility to identify and then free it. So, just as we need to request it, do it correctly, it has historically been a difficult programming problem. Because people keep forgetting things, like me. I keep forgetting things. I would think I'll probably Like I don't want to take this responsibility. I'm probably like having a lot of memory leak because I forget to clear up the garbages. So, we'll waste memory. If we do it too early, well, there's another side of the problem. It's like you erase something that you still need to use. If we do it twice, it's a bug too. Oh my god, it's so complicated. Exactly one LK with exactly one free. So yeah, only create once, only delete once. That's the key. That's the key of a good program. So what does Rust do? So the memory is automatically returned once the variable owns its code. So Rust is kind of do it for you as well, but Rust doesn't have a garbage collector. So how does Rust do it? So how Rust do it is that because everything has a scope, so when something get out of scope, it got erased automatically. Okay. So that's how Rust works. So it's kind of the third approach rather than garbage collection or ask the programmer to do it themselves. So Rust will also do it for you, but it used the scope to keep track of things rather than having reference and garbage collector to do it. Yep, so once it go out of scope, then it will be over. And because S is no longer valid, so you probably can already give this memory back from the string. Yeah, return the memory back to the allocator. It calls a special function for us. So Rust will already call the special function. It's called drop. I guess you can also call drop if you want to drop it early, but I guess like for beginners we should not do that. It's dangerous. And put the code in return automatically. Yeah, closing the curly bracket, so it's good. The pattern of allocated resources at the end of the lifetime. Resource acquisition. Why we have fancy terms? I don't like it. And also acronym as well. Like resource acquisition is initialization, RAII. The drop function in Rust will be familiar if you are used to RAII patterns. Okay, I am not familiar with it, so I'm not going to worry about it. This pattern has a profound impact on the way Rust code is written. It's simple right now, but the behavior of code can be unexpected in more complicated situations. We have to have multiple variables used. The data we are allocated on the heap. Yeah. So now we only like have one entry point, right? So it's very straightforward. What if we have like multiple? So we want to access this string from multiple point, then it will get more complicated. We'll see. We'll see. Variable data interacting with move. What's going on here now? So an example. Yeah, so 5 is x, and then copy of x, and I put it to y. Yep. So now actually we have two variables, right? So x and y, and they are separate, both equals to 5. Yeah. 2 5 values. So actually they are like 2 5 values. So if like for example I change x, well you can't change it here because it's not mutable, but like for example if x is mutable and I change x later, I think y will still be 5. Actually we can try it. I am a naughty person. I want to try it. Do I have a space to try it? Whoa, okay, maybe I try it in variables, I think. Yeah, do I have something here I can try? Yeah, so something like that. So let y equals to so if x equals to 5 and the x, so this is not relevant anymore, and if I print it out, so I want to print out x is x and then y is y. Okay, so if I save it, if I run it, so let me go to that, then I should get 5 and 5. So if I make this mutable, And if I do that and then I say x equals to 6, what is going on here? Yep, so y is still 5 because like at this point x is 5 and I make a copy of the value of x, which is 5, into y. So x and y are basically operating separately. Yeah, so x would be still y will still be 5 if we change x. So yep, that's what's going on. So now what if s1 is a string, s2 equals to s1? Whoa, okay, we're looking at this graph. Okay, so look at what's going on. So s1 is a string. So a string is actually a series of characters. Okay, let's see. Happening the string under the cover. 3 parts. So shown on the left, a pointer to the memory that holds the contents of the string. So this one, we have a pointer pointing to it. A length, so how long it is, and a capacity. It's a group of data. They store on the stack. On the right is the memory, and the heap holds the so this is a stack itself. So you would know like where it is. You would know how big it is, and then the capacity, like, and the length, right? So then you put that in a heap memory. The group of data stored on the stack, right? It's like the heap that holds the so there's okay. So the content is actually a pointer pointing to a heap. Okay, this is a string. The whole thing is a string. So there's like these are the metadata for the string, and they are all stored in a stack. But then within it, there's a pointer that points to a heap that basically store all this content, right? And the length is how much memory. So length is how much memory in bytes the content of strings are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. So they can differ. Yeah. The difference between the length and capacity matters, but not in this context for now. So yeah, it's just assume that they are the same all the time for now. They can be different, but just assume that they're the same. So what happened if we assign s1 to s2? Then the string data is copied, but the pointer is copied, but the pointer points to the same place, so the contents are the same. So in this case, if you, for example, change the H to a capital letter H, that will change for both because when S1 got copied, so this is S1, right? But S1 contained a pointer, so the pointer is only the address. The address got copied, but now we have S1 and S2 have the same address, but it access the same memory. So if we change one of them, the other will change. So that's what's happening, I think, right? Okay, so this look like. The result does not look like, yeah. Memory would look if Rust intended to copy the heap data as well. If Rust did it, so if Rust did that, if Rust also copied, then it would have a S2 should have a new address and hold a new set of data. They just got copied from here, from the S1's content. But Rust do not do this. Rust do this instead of this because, you know, if you have a huge string, right? If you have a whole like dictionary or something, then like it's very expensive because every time you do this, like then you copy another copy, then like, you know, you would blow up the memory very, very quickly. And also it take a long time to copy if you have a huge thing. So I guess most of the programming language won't do that. It's not good. Like the pandas data frame, right? You don't want to like have copy as default because then you blow up your memory. Yeah, so no, we are not copying it. But then you will have this like strange behavior that, like, for example, you do something with the pandas data frame, it returns the same data frame, and then you accidentally change it because of some, like, you don't know, it's like it doesn't got totally copied. So yeah, it's weird. So what happened here? if a variable go out of scope, Rust will automatically drop it, right? So but because here we are pointing to the same direction, what's going on? When S1 and S2 go out of scope, they will both free the same memory. So we would double free, which is not a good thing. One of the memory safety bugs we mentioned before, because again, rule of thumb, create once and then delete once. So if we, drop S1 and S2 at the same time, so we are dropping this 2 times, which is not good. It will lead to memory corruption. Whoa. So it's no good, because we may accidentally change something that's not supposed to be changing. Yeah, security vulnerabilities. So what if, for example, you S1, you drop it and it got free up, and then another program claims it and stuff, and then S2 you try to drop it again, then it will, corrupt the memory for the other program, which is not good. So after this line, Rust will consider S1 no longer valid. Doesn't need to free anything when S1 go out of scope. So this one won't work, because if we assign S1 to S2, then S1 will already automatically got the invalid. Then you can't use S1 anymore. Uh-oh. Yep. So what you need to do is to use clone explicitly, I think. Yeah. Shallow copy and deep copy. Yeah. Yeah, you see, it's kind of saying like, oh, you can't do this. Value borrowed here after move. Then I suggest to use the clone, but let's see what's going on. If you heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer, those are called shallow copied. Yes. Yeah, because it doesn't trace down what is also related and also need to be copied. So you just copy the first layer. That's what a shallow copy is. Yep, so what Rust will do is to make a shallow copy. S1 make a copy of the first layer, which is this 3 thing, into S2. And then invalid, so then this will grey out because it's now invalid. Was moved to S2. So it's just like changing the name. It doesn't have 2 anymore. So S1 rename as S2, and S1 is like, it's just rename, it's not a copy. So only S2 is valid now. S1 is not valid. So when S2 go out of scope, then we just free up S2. So that's what's going on in Rust. Never automatically create deep copy of your data. Any automatic copy can be assumed to be inexpensive, because we want it to be fast. So what the compiler suggests here is to use clones. So what does clones do? If we do want to deep copy, so it's basically the responsibility of making deep copies flow back to you, because it's a very expensive process. So make sure that the programmer know what they're doing and let's actually need to do it to make this deep copy. So using S1 clone is making a deep copy, I guess. Yeah. Not just the stack data. So it's a common method called clone. So it will be talking in depth in chapter 5. We may or may not get to it today. Yeah. Right, okay. Oh, method. Oh yeah, chapter 5 is about method. It's fine. Let's look at clone right now. So if we use S1 clone. So clone is, I guess clone is everywhere for a lot of different data type, because you need to make a deep copy. The strongest figure 4.3, I guess, is this one for 4.3. So it make a copy including the content of it. So after you call the clone, then you would have both S1 and S2, and you see a call to clone, then you know that something very slow, expensive, like it costs a lot of memory and very slow. It's happening. Visual indicator, something different is going on. So yeah, that's why Rust designed to not make a deep copy by default, but you have to use clone, so it's more explicit, and like the developer will immediately spot that there's something heavy going on there, and then we can investigate whether that is absolutely needed or not, right? Okay, so that's how the string got copied, if you want to copy it. Stack only data. There's another wrinkle. Woohoo! Using integer. Okay. Yep, this is valid. Yeah, we don't have to call to clone because we don't have a pointer in x, right? X is just a number, and it got copied. It's fine, it's 5, so it's just copy as 5. Yeah, it wasn't moved to y. We have a known size at compile time and store entirely on the stack, so the copy of the actual value are quick to make. Yep. No difference between deep and shallow copy here, so clone wouldn't work. Wouldn't do anything different. So you can use clone, but it's the same. But why do you do that? There's also a special notation called copy. Okay. So there's more explanation in chapter 10. The type implement a copy trait, the variable use it do not move. Trivially copied. So you can, so this technically there's like copy type, but Rust won't let you annotate a type with copy. If you have the drop, then you can't use copy. Yeah. Type needs something special to happen. Okay. So if you use copy annotation, you can't use the drop, so they can't be used together. Okay, documentation, okay. So nothing that require allocation, yeah. So that's why drop and copy is not, it should not be used together, because like if you have to drop some memory, then you probably have allocated the memory, then you can't copy, right? So if you use copy, then probably you don't allocate any memory, then you probably won't use drop. So that's why drop and copy should not be used together. So integer type, boolean type, and floating point type, character type, all these are copy, are not like, don't have any memory allocated to them. And tuple that only contains the copy type as well, because tuple is a combination of them. So if all of the components are copy type, then it's copy, but if it's not, then it's not. Ownership and functions. Passing a value to a function similar to those assigning a value to a variable. Passing a variable to a function will move or copy the ownership, right? Either copy the value or move the ownership. So some annotation showing this in and out of scope. Okay. So as coming to scope takes